Or tear out my hair.
There we go. All right, everybody, behave yourselves. Greetings, Earth and Space Explorers. Welcome to Doc Waller's Earth and Space Report for Friday, July 25, 2025. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a hot and humid summer evening here in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage, inform, and inspire people like you who are curious about Earth as a planet, who care about our life-sustaining biosphere, and who wonder about the greater cosmos and all that it has engendered throughout space and time. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, myriad Earth and space scientists, educators, and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, I'm honored to be once again hosting Dr. Sten Odenwald, a longtime colleague from my years at NASA's Goddard Space Flight Center. Sten has worked at Goddard since our time together in the 1990s. He received his PhD from Harvard University in 1982 and has since become involved with investigations of star formation, galaxy evolution, the nature of the cosmic infrared background, and the Sun-Earth connection. He has published more than 100 technical articles on topics as diverse as star formation processes in the Milky Way, Big Bang cosmology, and the impact of severe space weather events on commercial satellite systems. He is an active science educator and popularizer, having written several books and participated in many NASA programs in space science and math education. He has a number of websites promoting science education, including the Astronomy Cafe and Space Math at NASA. He has also appeared on National Geographic TV specials and other video documentaries. His most recent research involves chronicling the historic impacts of space weather on humans. Most recently, Sten was fired from his job at NASA, a consequence of the severe gutting of the agency by the Trump administration. So many gifted and dedicated people at NASA have felt the sting of these draconian cuts. That is why we need to show our support for Sten and his colleagues during these fraught times. And speaking of time, that is what Sten will be discussing during his presentation this evening. So let's get going. The Zoom platform is all yours, Sten.
Thank you so much, Bill, for that undeservedly flattering introduction. But hey, I'll take whatever I can get at this point. Okay, well, let me see. Let me get things fired up here. Here's a slideshow. Okay, I'll wait for all the menu bars to disappear, and then I can actually start talking. Okay, I'm going to talk about time. I've spent a lot of time thinking, our language is so infused with time referred words. You can't put a sentence together that consists of pure nouns. It's just gibberish. We need those verbs. And what you're going to discover is that a lot of our sense of time has more to do with how our brain processes information. And even the concept of processing sounds like it's a verb. But in fact, one can have processing that doesn't involve time at all, that involves statistical probabilities and things of that sort. So I'm going to kind of give you a kind of a worm's eye view of how we're thinking about time these days in physics. And it's complicated. Here's a recommended reading list. I'm going to start out with Oliver Stone, who spends a lot of time talking about the various kinds of pathologies that go on in the human brain that radically change our perception of time, sequence, anticipation of events, organizing events in memory and in temporary memory, and so forth and so on. Then we have a wonderful book by Julian Barbour talking about the end of time, where basically time is completely annihilated. And you're going to have to read the book to understand what that means. Finally, we have two string theorists, Lee Smolin and Carl Rovelli, who basically take opposite views of the fundamental nature of time and whether time is a fundamental ingredient to the world. In one case, space is viewed as fundamental with time being derivative, and in the other case, time is considered fundamental with space being derivative. So you get both views. And of course, to help you as best I can sort all these things out, and I got to tell you, there's been a lot of work on this subject in the last 30 years. Some of it is borderline incomprehensible unless you're a specialist in quantum theory and relativity and a whole host of other subjects. So basically what I've tried to do is to digest as best I could, some of the threads that you see in these many, many books that are out there into sort of a short, pass the French fries, please, kind of introduction to time from many different directions. Hopefully one of those directions will engage you and resonate with you, and you'll walk away with, oh, that helps me understand the confusion a little bit better. Well, let's start with St. Augustine. What is time? If nobody asks me, I know what it is, but if you ask me to explain it, I have not the faintest idea. That's a paraphrase. We all understand what time is, but if you try to explain why it is, you go down a rabbit's hole of bizarre logic and circular thinking and stuff like that. Einstein helped a little bit, I think. The only reason for time is so that everything doesn't happen all at once. Okay, that sort of works, tongue in cheek. More importantly, time and space are modes by which we think and not conditions in which we live. Now, that's a real head scratcher, and hopefully by the end of this 6-hour talk, you're going to understand a little bit better what that's all about. I'm just joking about the 6 hours, but it's going to seem like that. Lee Smolin, time is described only in terms of changes in the network of relationships that describe space. This perspective is a complete product of relativity theory, which has been the preferred way of looking at how things work in our world for about 120 years now. And the result of relativity is that you wind up with Einstein's theories, you wind up with quantum field theory and its ability to predict things with high precision, and so forth and so on. Relativity is all about relationships between things and not in terms of absolutes. The only way we understand space is in relation to objects and the relationships between those objects. There isn't some fixed coordinate grid in the universe that things reference themselves to. That's the old Newtonian view of what space and time are like. Okay, so let's talk about subjective ideas about time. Well, we have an understanding subjectively that time is different from space. I don't need to belabor that point. We all kind of understand what that means. Time is a series of moments, okay? I think we understand that too. There is a past, a now, and a future. We have a firm feeling that that's the way things work with time, that there's the moment that we're experiencing right now, which is different from the moment that we're experiencing right now, which is different from the moment we're experiencing right now. And those moments come to us from the future and go into the past. That's sort of the general flow of things from the future into the past, and they go through the now. And that's what I mean by the future flows into the past. And the speed at which time passes depends sort of on your state of anxiety or your emotions. And I think we've all had experiences where time seems to freeze or slows down enormously when we're in crisis or in duress. That's all subjective stuff. It doesn't tell us anything physical about time, but it tells us something about how we experience it as humans, as organisms. Now, the objective aspects of time are a little bit more odd. Relativity says basically time and space are blended together. Okay, you can't separate space and time as physical things. Right now, I've got to somehow minimize. Oh no, that was bad thing to do. How do I get back? Darn it. I tried to minimize the faces of people so I could actually see the text underneath. All
Go
right.
back in time.
Oh, here we go. Here we go. Okay. All right. All right. Objects experience time uniquely. If I have two wristwatches on my wrist, they technically do not pass time the same way, even though they're separated only by a few centimeters. All right. That's a physical fact that can be demonstrated. Time does not exist inside atoms. I don't want to belabor that very much. Time and entropy change in the same way. And in fact, time and entropy, the way that time passes and the way that entropy increases, are sort of interchangeable ideas in physics. Time did not exist before the Big Bang, and here's that problem with using, verbs, to talk about things. What do you mean by before the Big Bang if the Big Bang is when time and space were created? So, we get into these logical things because we try to translate the physical theory into the nouns and verbs that we're familiar with using. Time does not exist outside the universe. I may or may not have the opportunity to discuss that in a little bit more detail. All mathematics is timeless. Okay, that's an important point. There is nothing about the mathematics that we use to describe events in the universe, even as simple as a tennis ball in a tennis game and predicting its motion. There is nothing about that mathematics that identifies a specific instant we call now. In fact, it's a timeless equation. It has t in the equation, but it's just a variable. And so mathematics is timeless. The properties of triangles, Euclidean triangles, is timeless. And it's a curious thing that we're using mathematics, which is a timeless system that we've created to try to understand things which operate in time and for which we have a distinct appreciation that there is a now, that there is a past, and there is a future. All of the mathematics has nothing in it that says anything about past, now, and future. And the objective nature of time is that now doesn't exist. Have you ever wondered why it is that you were born and are experiencing the world in the current now? Why aren't you living at a time when the pyramids were being constructed, or hundreds of years in the future when we're colonizing, Mars and doing other things? Why are you inhabiting this now in the universe? There is nothing in physics that tells us why one now is favored over another. And that is a long-standing philosophical and physical puzzle that has yet to be worked out. It's the problem of now, or the specious now, as you might hear philosophers talk about. But we do know one thing. The subjective world of the brain and the neurons is embedded within the objective world. So somehow, whatever time is, it affects both of these regimes the same way. And so the answers to what is time essentially have to come from understanding the objective world rather than thinking about the subjective one within our brains, which can be riddled with, false understanding, fantasy, imagination, and all sorts of things like that. So anyway, here's another puzzle that we have. The picture on the left is what everybody will see when they look at a sunset. I mean, you'll see a riot of colors. On the right is what actually is being presented to you. Nature doesn't have color, okay? Color is what we call a qualia. It's a feature that is added into our visual experience at the retina by the way that the brain processes this retinal information for one reason or another. One hypothetical thing that might be going on is that the brain discovered that water reflects in a certain wave band, and water is a really cool thing to be able to see in your environment. So the brain tags things that look like water by giving it a color which we call blue. Red is not a very good color because if you're herbivores, that means you're talking about leaves in the fall that are dead that you can't eat, or fire. So red tends to be a color that the brain might colorize the world in, to show you where things are that are tasty and where things are that are fire, stuff like that. So, and things that are green, well, that's really cool because herbivores really like green stuff. So the brain figures out, from the wavelengths that it's presented, what the wavelengths look like that represent nice, healthy green leaves. And it basically creates a qualia called green, which helps us code for that particular feature. So maybe it is that the reason that we have color is an evolutionary thing, and it's irrelevant, what the experience of color is. It's a way that the brain has figured out of tagging the electromagnetic spectrum that's presented to us in a way that's beneficial to survival or to having a good meal or not getting burned up. Okay, now what do we have going on here? We have, all of a sudden, I can't change this thing.
It seems to have magnified.
And I don't know why it's doing that. Son of a gun. Oh, there's an icon down here that has a shoot. All right. Okay, good. We've got a pretty good idea of how our brains create the sensation of time, believe it or not. All right. It seems that the brain chunks information into like 3 categories. We got memory. Everybody knows what memory is. We have forecasting, which is anticipating things. And then we have now, which is the present. And so what happens is that we understand how these things work because there are various pathologies that interfere with those things. And so we can logically work out exactly what is required in order to experience time, irrespective of the kind of pathologies that you might have. And so normal brains, we can figure out what normal experiences of time should look like. So it's very cool. In the now, which can last up to 3 seconds in clock duration, if you want to use that as a measure, sensory inputs can arrive at any moment, and they're perceived as having occurred at the same moment. There's no master clock that organizes sensory input. It's just run on kind of a lot of random things going on that are brought to the attention of consciousness. And basically, it's kind of a Hail Mary process. Whatever sensory information, seems the most vital for survival, that's the one that you experience more keenly for the now. The interesting thing is that because of neural latency, you have within the now memories, latent memories of what just happened in the past. And there's an interesting leak through from the future where the brain is doing the processing to anticipate what's going to happen next. And it basically brings some of that into the now as well. So now is a mixture of things going into the past and coming into the moment from the future, from processing and looking for patterns that might have good survival aspects. So that's why now seems to be so fluid and why we have this sense of time actually flowing. The brain is spending some time forecasting based on its current sensory information, what's going to happen next. Anything that seems interesting or good for survival, it will tend to preserve that information in memory. And so the net result is that you have leakage from the future into the current now, and you have a latency memory of things in the past into the current now. And the overall sense is that you have a flow from the future into the past through now, which is the present. And so that's generally what neurophysiologists say is going on and why we have this interesting feeling of time passing and the flow of time. Now you can think about these little memory now prediction chunks of processing as little processing steps. It takes a whole lot of them to drive a car down to your local store. It also takes a bunch of them to learn how to evaluate a simple equation. If any one of these steps is destroyed or interfered with because of stroke or some kind of chemical imbalance, all of a sudden there are some skills that you probably will not be able to carry on. So we know that there's a relationship between this flow of information from the future through the now into the past that is involved with, training you how to do different things. And it's like, there's this thing called the Jacquard loom, where they had like these cards that would go past bobbins in a sewing machine, and each card is different and keyed to a particular pattern that was supposed to be, built into the cloth as it was woven. Well, that's kind of the way the brain seems to work. Each one of these memory now predict things is kind of like one of these cards going by, and the net effect of these cards going by is basically that you learn how to drive a car, solve equations, write poetry, figure those things out. So basically what we now need to do to figure out what time is that we have to figure out how it's basically subjective and objective, and then try to find the objective aspects of time that help us better understand why it is a thing. I mean, that's really what the basis of this talk is all about. Why is time a thing in the physical universe? So anyway, we can kind of compartmentalize this. The objective world is universe, laws, matter, and atoms. And the subjective world tends to be about chemistry, neurons, and consciousness. Oh, by the way, consciousness is another one of those things that's almost like color. However, the problem with consciousness is that people are trying to understand what consciousness is and how it works. But the problem is that you're inside of it trying to look out at yourself being conscious. And that's really hard to do. And so we're struck with the same kind of problem in thinking about time. We are built, our brains are built to exist in time within this flow that our brains and our neurons and synapses create. But then we're trying to step outside and look back at ourselves experiencing time from inside the thing that is creating the sense of time. So you can see it's horribly, mixed up. And that's why it's taken so long to even begin to sit down and figure out what the basic rules of time are, because our brain always interferes with that by insisting on looking at everything through, verbs and nouns, whereas time might not be either of those two things. Here's an interesting problem. I said before that mathematics is timeless. Here's a case where the mathematics of essentially the wave function of an electron inside of an atom. This is Schrodinger's equation for those of you that are cognoscenti. This equation has no indication of time at all. It's all about space and about probabilities. That figure that you see on the right is what the electron looks like in a particular quantum state that is identified by the equation on the left and solved for a particular case of energy, angular momentum, and spin. The problem is that electrons don't move inside of atoms. We have been laboring, even our classrooms labor under this idea that electrons are like little planets, orbiting the central nucleus. And no matter what we do, we still can't seem to root out that fundamental misconception about what the heck is actually going on inside of atoms. It's such an intuitively reasonable thing to think about that it just stays there. But in fact, when you solve the equations over and over again, you see that the electron is everywhere and nowhere, quite literally, inside of the atoms. And there's no movement because it's being a wave. It's being a standing wave within the boundaries of the energy well that represents the proton. Here's a case. This is a static image. I'm not sure how many of you can actually see what's going on here. Can you all see that there's some kind of a movement going on?
Yes.
Okay, good, thank you. This is not a GIF. This is not a GIF movie. This is a static image. But your brain is processing what it sees as a static image as movement. And only our brains see this. All right. Objectively, nothing is moving in this image. This is what I mean by some aspects of our world are qualia and others, are probably not. But we can identify the qualia because, well, in this case, we see motion when there isn't any. And in the other case, we see color when nature actually isn't providing any color information whatsoever. In relativity, the problem is that space and time are inexorably blended together. There is no such thing as two things being simultaneous or systems of matter being simultaneous in the universe. Time is a local thing that's carried by a local clock that you happen to be carrying. It's not something that's a global feature of the universe. So there's no such thing as isolating a particular moment in time from features in space. It just simply doesn't work because they're so terribly intertwined. And because of this intertwining, we call the entire shebang, we call it space-time. And we think in terms of space-time as sort of like this block. And you can slice it in certain ways and see one kind of thing going on. And in other ways, depending on where you are and how you're moving, you'll see different things going on. All right. This is what we call the block universe. I mean, I can spend an entire talk on nothing but this particular way of looking at the world. The problem is that it's a completely, sort of, this is not the way space-time actually looks. It makes you think that that time goes along the fourth dimension, which is like this horizontal axis, and space, represented by these two-dimensional slices of the three-dimensional universe, is where every particle of matter is at a particular instant in time. The problem is that every point within that spatial slice is experiencing time differently. There is no cosmic universal time that is being kept by a cosmic clock somewhere where you can actually slice space-time into these nice, mathematically perfect space slices. Space and time are always mixed up together, so those sheets that you see there, which are supposed to represent where everything is at a particular instant in time, are actually very distorted, folded around, bent, warped, pockmarked by all kinds of strange things going on. And just as I was saying before, if you have two wristwatches on the same wrist, they do not keep the same time. They are located in two spatially different places on your wrist. And because there is a difference in space between where these two clocks are, general relativity says there is going to be a difference in time that cannot be overcome by trying to synchronize them. If you try, you'll get them working together for a couple of beats, and then they will slowly drift apart. And the other thing is that clocks actually don't measure time. They measure a unit, which is a space-time unit. And that's why in physics, it's so hard to sort of separate your measurement of time from a particular measurement in space, because they're basically blended together. We can imagine things being very controlled and very carefully set up, like these sand clocks. But the problem is that each one of those sand clocks is located in a different place in space. So when you claim that you're taking a snapshot of all four of them at a particular instant, in fact, you're not. Each one of those clocks, you're seeing its time at a different time. So the only thing that you can say about these images is that in the left-hand image, the sand is in state 1. In the right-hand image, the sand is in state 4. And there is some kind of change going on between each of these states that is partly space and partly time. But it's not something that is going to be carried by a clock or measured by a single clock. We can try to do it, and we're discovering something interesting, that you can have a clock that a digital clock is a good example, that measures some kind of an interval. And then we can tag each of these intervals, each of these images of the sand clock with a code that comes up on the clock And then we can organize them into some kind of ascending order to represent maybe the passage of the changes going on. But that's about as close as we can get to talking about time in any kind of a direct way. Ultimately, we're left with changes in things occurring in space, and then using other things that change in space called clocks to tag the things that we're studying. All right. The other thing that's interesting is that we infer the existence of time by using relics that are stored in three-dimensional space and a logical ordering of them, usually cause and effect, along a fourth axis that we call time. Now, this is an organization of things in space that our brain really likes. And in fact, now we're in a situation where, what comes first? The brain, in experiencing or telling us that it's experiencing a qualia called time, is changing its state from one moment to the next, and then using that change in state to tag things that we see in the outside world to give it the impression that other things are actually changing in time, which we're using as an internal thing. So that's kind of like, we invent color in our brains, and then we go and organize things in the outside world according to their colors, even though things in the outside world don't actually have color. Here we have a set of relics that are along the fourth dimension. Okay, we have a monument, we have a fossil, and we have a photograph. Now, how do we order these things along the fourth dimension? Okay, well, this is how we logically order them, because we have some rule and some idea about what comes first, and we have some idea of cause and effect. And so we use these things that our brain provides to organize spatial things and relics that we find in our world according to this particular scheme. And that really is an interesting sort of thought about what history is all about. Ultimately, because we exist in the now, history is all about relics in the past that exist in our now moment. Those relics can be the pyramids, they can be books, they can be a variety of things, but we organize those things that we perceive in our now according to a particular cause and effect relationship that we've all agreed on. Historians have agreed on how you interpret things in terms of something called history, but ultimately, history is just a bunch of relics that we see in our present moment that are organized according to a particular scheme that we interpret as time, but it doesn't necessarily have to be a time ordering of things. My current now, in my current now, I have a diary for a particular day in 1975. And I spent 100 nows of my present time reading my inscription. And the inscription was, "Time rushes on, and before too long, only my memories will remain of the wonderful times I've had. There is immortality of a thing only in the memories that you have of it." Kind of a profound thing for a 21-year-old to have written, but I was pretty cool back then. But it's sort of this idea that I can reach back through this relic, which is a diary, which I still have in my physical possession, and I can read something that is tagged by a date at the top of the page as August 17, 1975. But, the issue is, how did I know that that event actually happened? How do I know that this relic that I'm looking at is actually the original relic that I wrote, ostensibly back in that time? And so now, you have this issue that, if we rely on relics and our understanding of how to organize them as our way of experiencing long periods of time, in the past, that means that it's very fallible. And in fact, it's not unusual for historians to have lots of controversies over the ordering of things. There are inscriptions in various Egyptian tombs that ostensibly give listings of the names of pharaohs, We interpret that listing as a chronology of pharaohs, but we have no independent, objective way of really assessing whether or not Pharaoh A actually came before Pharaoh B. To do that, we have to find other relics in our world in the current now that help resolve that question. Okay, so that's the dilemma about creating history from relics, and you can read a lot more about this by reading Julian Barbour's book, where he says that the only fundamental thing in the world are these relics, and the thing that knits stuff together into what we call time is that the more relics that you have in the current now, the more likely the current now is to actually be realized in some grand scheme of cosmic unity. All right. And you're going to have to read the book to really understand what that's all about. But it's a really engaging way of thinking about, how things are not organized in time at all. They're just random. And we have these ways of organizing these random things through relics that give some of these things higher probabilities than others. And so our history consists of relics which allow some kinds of things to have higher probabilities than others. And so history is just an organization of these higher probability things that we call time. But anyway, here's an interesting thing. Real museums are places where time is transformed into space. I love this idea because here's a whole museum with relics. And there's a little bit of information in each of these relics so that you actually can stand in front of one of these displays and kind of figure out what came first, what came second, what the cause and effect relationships were. But it's not that easy. It's not easy at all. And there's not necessarily a unique history that describes these events in a sort of a coherent way. One of my favorite science fiction lines, other than the one from The Day the Earth Stood Still, where he said, "This is not your planet," is Roy Batty when he said, "All those moments will be lost in time like tears in the rain." And that is extremely evocative of the real dilemma, because these moments are coded literally in the relics that we find around us. And eventually these relics disappear because of erosion and wear. Now, I have used a lot of very sloppy words here. Erosion and wear sound very time-like. So it sounds like I'm sort of in a circular way talking about time as not existing, but on the other hand, I'm using words and analogies that sound very time-like and organized. And that is the essential dilemma of even talking about the subject, that there is so much going on at the same time that you have to be careful. And it's really quite interesting. Why is space so different than time? We have this sense that you can do things in space, but you can't do the same kinds of things in time. You can travel just about anywhere in space, but you're dragged inexorably, into the future by time, and you don't have a whole lot of freedom, except in relativity. You can kind of slow down the rate at which you're going forward in time, but you can never reverse it. Change doesn't necessarily imply time. There are many examples where things change, but they don't have a time-like character to them. If you've ever looked at a mountain, you'll notice that there are some species of plants at the base of the mountain, and then the number of species seems to decline as you get closer to the top. So in fact, you can count the number of species of plants as a function of the altitude, and you'll notice, as the graph in the top right shows, that there is a change in the number of species with altitude. Okay, you can also illustrate this in the figure at the bottom right, where you look at slices of space, through the mountain. These are two-dimensional slices, and you stack them up by altitude. And instead of coding them by, time, you basically code the number of species you find by altitude. And that turns out to be a much more useful way of characterizing the plants on that mountain than time. Altitude is far more important than time in organizing the information that you have about species. And that has a direct sort of consequence for how we look at the world around us. There are many ways in which our brain can sort of fabricate things in the world and organize them, but it finds that there's one particular way of organizing things that really seems to have good survival aspects to it. I'm going to sort of sneak up on that subject a bit at a time. All right, so our world is four-dimensional, and why is time different than space? I'm showing you a three-dimension, actually two space dimensions and one time dimension, because I can't draw in 4 dimensions. So we've got these little dots which represent things, and then we're going to change which of these axes we're using to represent the thing that we call time. And let's take a look here. All right, here are these axes again. We're going to look at along one axis, the x-axis, we're going to look at snapshots of the world in the y and z plane, all right, at 3 different states along the x direction. And we see, you know, as you go from state blah to state z to state something, I mean, I'm not going to characterize those with 1, 2, and 3 or time, because that might not be a relevant thing to use. You see that basically the states all look the same. There doesn't seem to be a whole lot going on. It looks all random, no matter how you slice things along the x-axis as you're looking at the YZ projections. We can do the same thing along the y-axis. This time we're looking at how things are projected in the XZ plane. And again, you know, these 3 states look pretty much kind of random, not a whole lot going on. Now let's look at the next one, if we organize thing along the z-axis and look at the yx snapshots. All of a sudden, a pattern seems to emerge. Okay, so what this shows is that if you have, you know, these 3 dimensions of space or 4 dimensions of space, and you slice 3 of them along one of the axes, if you do that for 3 of those axes, you're going to get random dots. All right, random dots suggest that there might be a change from one state to the other, but it's chaotic, it's random. All right, this, you know, could correspond to the idea of, you know, random images and memories, unpredictability. No genes are passed on as information, because if there's randomness involved, sometimes they're passed on, sometimes they're not. And the organisms go extinct, you know, if the world is organized in that particular way. But look, if we organize it according to time, all of a sudden we have a sense that states 1, 2, and 3, you know, have an ordering to them that increases the amount of information and structure as we go. In these disorganized spaces, there is no possible way of having a sense of past, now, and future, because the states, as they change from one state to the other, the resulting changes show random points of information that don't add up to anything organized and coherent. But if we organize along the 4th dimension, all of a sudden things look interesting. There's predictability. Predictability favors survival, and certainly favors the idea that there's a past, now, and the future, because now things are coordinated and organized in a way that we can interpret as time if our brain wants to process states 1, 2, and 3 as changes along that particular axis. So here we are at the Big Bang. Initially, the story is that the universe and the energy was changing in all 4 space dimensions at the same time. You know, it was just random. But then we entered a state where 3 dimensions remained space-like, but one made it very easy to label space states in terms of progressive complexity and increasing entropy. And for some reason, the universe liked that. I mean, there are 4 ways in which things could have started out, and we're living not in the universes, the 3 universes where you wind up with randomness that disfavor life, But we wind up in the universe where we have a definite fourth dimension, where things are organized, where entropy increases, where complexity increases, and that's where we live. So in a sense, there's a kind of an anthropic element to why we have time. Time is an organizing element along one of the four dimensions that just makes it easier for survival because it favors changes in states that are in a regular way that lead to things like laws, laws of nature, limited predictability, and all these things favor life and life learning strategies for how to find food, because you now live in a world that has a lot of inherent logic built into it because of this progressive change in complexity that favors, one axis out of the four in which things change. So when we take a step back and ask, well, what's going on, even at the quantum scale, now we enter the domain of what's called loop quantum gravity. This is the area that some physicists are working pretty hard at. It's sort of a competitor to string theory, but it has a kind of an interesting aspect to it. It begins with the idea that space is quantized. Space only exists at, say, these specific points, and anything in between is literally nothingness. However, those space locations are organized together, much like if each one of those points was a cell phone, somebody with a cell phone, you can imagine those networks drawn in these lines as sort of being communication channels between various cell phones. Now, the really cool thing is that it takes a lot of energy to keep a really big network with a lot of connections going. It doesn't require nearly as much energy to keep smaller networks going. So that translates directly into why do we live in a four-dimensional world? Because with a four-dimensional world, you have a very small number of nearest neighbors. But if the world were 10 or 100 dimensional, you would have an awful lot of nearest neighbors. And apparently that costs energy. And so to favor lower energy configurations, the process tends to favor lower dimensional configurations. So that's sort of a very breezy explanation for why we live in a four-dimensional world and not a 50-dimensional or 1,000-dimensional world. It's just very expensive energetically to maintain all those nearest neighbor connections, at the quantum scale, if the dimensionality is too high. So quantum gravity, they can create essentially snapshots of space, which they call spin networks. And each one of these spin networks is basically a timeless snapshot of space. Just like the wave function of the electron that we see on the far right is a timeless snapshot of what the electron is doing. There's no motion there, just as there is no motion in the other two examples that you see there. But in loop quantum gravity, changes happen along this fourth dimension, which they call the direction of change. They don't specify that it's time, it's just another dimension of space, but in which changes in things can be stacked up in a logical way, which you could sort of infer to be like cause and effect. It also turns out that the way in which these things are stacked also mimics the idea of entropy increasing along this particular dimension, right? So you start out with a fewer number of states and you wind up with more possible states as this process of change continues. So what happens somehow magically is that these changes in space along this fourth dimension become interpreted by us and quite literally by the universe as changes in time. And our brain basically also follows suit in the same way. And so we interpret these changes in states from one state to the next as the passing of time. just as we interpret qualia like particular wavelengths as red. So the brain is sort of designed through evolution to take full advantage of the direction in which things change in an ordered way, and that's the direction in which time passes as well. And there's a whole lot of discussion you can get into about how entropy, which is the change in the number of states in the direction of essentially more organization at the expense of less organization elsewhere, how that leads to sort of a time-like aspect of the world. So there are four possible ways that three-dimensional states could have organized themselves in space-time. And we live in a universe where the fourth axis was the best way that led to what we see as cause and effect and the physical laws. Anything else, any other slicing of this four-dimensional thing along any of the other three axes would give you basically randomness, chaos, and maximum entropy. So there was no opportunity for organization to really set in. So that's a good thing, because we live in the best of all possible universes. But again, this is a circular argument, because life could not have occurred in these other universes where the other slicings were in effect. So we live in the one which provides a unique time axis, which is pointed in the same direction as the direction in which entropy is increasing from the Big Bang to the future. And so in a way, the discussion about time is a discussion about almost talking in a circular way, but not quite, because we've introduced a few new things to the discussion that might help at some point in the future to resolve what this is all about. Unfortunately, what we're learning in cosmology is that there is a role, a limited role, for what's called the anthropic cosmological principle. And that is that the universe looks the way it does because we happen to be here observing it, right? And that means that in order to observe it and be conscious, you have to be something which can survive within the physical laws of that universe. So it's a kind of a circular argument that we're part of a universe in which the initial conditions were set up in such a way that made us possible in the future, so that we can look back, and sort of be amazed at how unique the universe is. If you talk to string theorists, they're still trying to find our universe within a landscape of 10 to the 500 possibilities, which they call the landscape. There doesn't seem to be a unique, logically consistent equation that gives us only one universe. Instead, it gives us a landscape, a statistical ensemble of huge numbers of universes with huge numbers of choices of fundamental constants and particles, and slicings of time and space. And we're in a sort of a subset of these possibilities where, we have the experience of time, and our brain adapts to that by giving us a qualia, which we're all very familiar with as to the passing of time and our experience of it locally. And so is time travel possible within this new way of looking at things? Well, not quite, because only relics of prior states exist in your now. And so time travel would be like trying to step inside a photograph, and you can't do that. So that's the thing, that in the what's called the eternalist model, which is this block universe of relativity, all times and all events are still in existence, and our consciousness is just following along some kind of a world line, and consciousness is sort of seeing things, presented to us, but all these things exist and will always exist. Well, that doesn't have anything to do with the experience of now. The now experience is more like, we have randomness going on in the future. There's some way in which we can predict things. That randomness is like a statistical distribution of possible futures, in which we have something like free will, to make a selection about which future states we actually want to inhabit. That doesn't exist in the block universe. The block universe is everything is already done. There's no free will. So that's the dilemma that we have. If we talk about time, it's got to be discussed in a very different way than what we've normally sort of tried to do before. And the idea of free will is very intimately connected to, what the possibilities are. So that basically is it. And I think I just squeaked by in time. Yeah, 8 o'clock. Wow. I could have gone on for another 4 minutes to recover my lost time at the beginning of the talk, but that's fine. Anyway, if you got any brief questions, I'm expecting a deluge of but what ifs and what about this?
So anybody who wants to speak, please feel free to unmute yourself.
Yep.
Yeah, I want to ask about the idea that there's no time inside atoms. Then how do you explain atomic clocks? And you presented the Schrodinger equation. You presented the time-independent Schrodinger equation. If you'd presented the time-dependent one, and if you have a varying potential, of course, you have atoms undergoing transitions, and that depends on time. So I don't quite understand what you're saying.
Well, it all comes down to, right, that's a very fair comment to make. When you look at the wave function for the electron in the atom, if it's not subjected to anything, it's just going to sit there and not move and not change, right? And that's the essence of these states being stationary. And that's what I mean when I'm saying that time doesn't exist. I mean, once an electron is in a stationary state, it's literally, sort of colloquially, it's everywhere and nowhere within the atom. It's not moving from one place to another. Electrons are not point particles anyway, although we like to characterize them that way because of this planetary model. And we don't think very well in terms of matter being a wave, so we don't have an intuition about what that kind of an image ought to look like as a replacement for the orbiting electron. So when we talk about solutions to Schrodinger's equation, we're talking about stationary states in space at a particular moment in time, which is the coordinate that we use that tells us
that's the time independent of Schrodinger equation. So of course you're going to get stationary. But the Schrodinger equation, the proper Schrodinger equation, or the complete one, has time. So, and having a stationary states doesn't represent real atoms in the sense that there's always some kind of interactions that results in changes in the atoms, and then you get atomic clocks because of those changes. So,
well, that's there is quite a lot of work that's being done on the nature of time at the quantum scale. I mean, we have entangled states, and we have a variety of new ideas, that sort of help us understand that a bit better. But it's the best I could do.
Thanks.
Arthur has a question.
Yeah, I've always got a question. I can't get my camera to go back on, and I'm not asking you to fix it. No, the question I've got is, it almost seems like time is scale dependent. I mean, things that happen very quickly, we're not aware of. Things that take a long time, again, we're not really aware of. I mean, unless you're going to live a million years, you'll never know something happened. So it's kind of dependent on where you are, how big you are, and what you're able to observe with your ability to observe. And lately, we've gotten pretty good at looking out into space better and looking down at the atomic level. When IBM was doing the videos showing atoms, I thought, well, that's pretty good. I mean, I'm working with stuff at work all the time. Now you can see it, just because you can illuminate it. But it seems like time is very scalable, and you got to be at the right scale to appreciate what it is.
Well, I mean, we live in an infinitely creative universe that has things literally going on at every scale. They don't change according to a set master clock, because everybody basically carries their own proper time, even down to the level of atoms. So, this idea that you can somehow slice the world into snapshots even on a scale more than a meter across, I mean, is really quite something. You used to think, oh, okay, well, we can run a clock on the Earth, and we can calculate planetary positions well enough to send spacecraft there and get them within a meter or two of their landing places. And that's fine, but that's not what we're talking about when we're testing general relativity. General relativity has to be tested at many different scales. Currently, the idea that you can have simultaneous clocks at any scale is completely wrong and flies in the face of what we understand about even special relativity, let alone general. General takes into account changes in position, and basically gravitational field that also influences, time. You can have stationary clocks in a gravitational field, and they will gain or lose time just as surely as if they were in motion under special relativity. It's location and position within a gravitational field that also causes time to get pulled out of synchrony with clocks that can be as close as a few centimeters apart on the surface of the Earth, a few meters apart further away from the Earth, or it can be pulled apart very easily near the event horizon of a black hole. So, time is very fluid, and there's no such thing as synchronizing clocks on any kind of a scale. Which means that you can't take space-time and slice it into pure space-like surfaces that are three-dimensional, because there is no uniform time along which you can do the slicing. And that is the big dilemma that's present, not just at a cosmological scale if you're trying to do a snapshot of the universe, but also at the millimeter and centimeter scales from what we could test with atomic clocks.
Sten, your comment in 1975, it puts you being born in 1954?
52.
52. All right. My math is worse.
Yeah, I have a couple of relics that show that I was present in 1952. One is allegedly a birth certificate, and another is a photograph that's dated, and a third one is a plate, a brass plate that has my name, but it doesn't have my likeness. So I assume that's me, but I can't be completely convinced that it is. But they all hang together in terms of a coherent story. So I kind of go with the story.
I would have thought bronze baby shoes.
Yeah, I got those too, but they're not dated. So I don't know when they were produced.
It's a genre thing.
And my parents are no longer with me, so I don't have their memory access to probe that validation either. I'm making this sound like it's a joke, but it's not. This whole idea of how you verify history is a very, very deep subject, and Julian Barbour really messed things up enormously by fundamentally saying that dinosaurs never existed. All we have are relics, and those relics can mean anything depending on how you interpret them.
Well, religion didn't help much either in that regard in some instances.
Yep. So anyway, yeah, I hope I didn't mangle the topic too much, but it's an easy topic to mangle on many different scales.
I want to thank you very much. It's a great lecture.
Oh, well, thank you.
We've had a little discussion in the chats about radioactive decay and the half-lives associated with radioactive decay. And we were wondering I was wondering in particular how that would square with this idea of time being basically a figment of our imaginations.
In radioactive decay, you have two states of the system. One is before the tunneling event, and the second state is after the tunneling event when you have a free alpha particle. There's no time associated with these things. So it's very hard at the quantum scale to really identify when things are happening, because it's all about the wave function of the alpha particle leaking out of the energy barrier, and that can happen at any time. We characterize it as a half-life because we have a device called a clock, that seems to be able to, sort of uniformly identify things according to a time ordering, which we call a time ordering. But the process is a quantum mechanical process. It's not one that's dictated by time. That's why you can't predict when a decay will actually occur. I mean, fundamentally, there's no time involved that's a unique time. There's only a statistical distribution of times.
I think that's what Phil Schwartz was getting at, in that it's a statistical outcome.
Exactly. Yeah, there's no clock. There's no clock that beats out and says a free neutron is going to suddenly decay into a proton and a positron and a neutrino, after exactly 660 seconds have elapsed. It's all a distribution, and it all depends on barrier energies and what the wave function of the particles look like, that are bound by the strong interaction. And
right. The individual decays are completely stochastic.
Yes.
It's in the aggregate is the only way that you get the half-life.
That's right.
That statistically, we can tell that this supposed Vermeer is a fake, right? Because
exactly right. In the aggregate, we can measure a uniform time on the surface of the Earth to a tolerance of maybe a few, microseconds, and not worry about general relativity or things like that. But once we get down to nanoseconds for GPS satellites, then all of a sudden the location of the clock in space, in the gravitational field, and its motion become extremely important in determining what time it is.
Right. It's a good thing that the speed of light is as big as it is.
Oh yeah.
so that at the scales of space that we live in, the errors introduced by difference in location of clocks and so on are so tiny that they're now negligible. And you only see, one of the most beautiful things, I think, that are little nuggets I've picked up in the course of my education about the physical universe, is the high energy muons that are created in the upper atmosphere by cosmic radiation. They are traveling so fast that their experience of time is so slow that they make it to the surface of the Earth.
That's right.
I think there are a number of experiments going on where they're actually, burying devices to detect muons at various depths below the surface of the Earth, and actually, being able to use the density of those things
the thing that's the most interesting is they now have clocks that are so accurate, I guess, or sensitive, that you can measure gravitational time dilation across the width of the clock.
Wow.
One side of the clock is measuring time slightly different than the other side of the clock, but it's the same clock.
Yeah.
When we're down at the level of attoseconds,
the
fact that the gravitational field and the height of one part of the clock is different from the center of the Earth and the other by only millimeters is enough to pull parts of the clock out of synchrony with itself.
That's because the speed of light is very large, but it is finite.
Right. Yeah. So anyway, that's, clock synchrony is not something that's achievable to any degree of precision. We can, up to a certain degree, synchronize things and talk about, sending people to Mars, with an accuracy of a few meters when they get there, and all that. That's fine. We can also talk about the evolution of the universe in chunks of, a million years, at a time, because over a million years, all of these different clocks are going to roughly receive the same answer. And the important thing is that every single chunk of matter that came out of the Big Bang is carrying its own proper time. And that proper time clock, every single one of them agrees along each one of these world lines that the universe came into existence for 13.8 billion years ago. They are all going to measure exactly that same start time on their many, many, many different clocks. Even though comparing the numbers between them is going to depend on, one observer being in a higher gravitational field than the other, and one being in motion relative to the other. But all those things don't mean anything when you're referencing everything to proper time, which is the clock that I'm carrying on my wrist, and that everybody carries, separately. Even protons have their own proper time that's different than the next proton over.
Yes.
Well, all this makes me feel better about having been late to various events.
But the thing that's so amazing is what's going on in brain research and this whole idea of time being a qualia, just like color. It's a persistent and very, very useful way for the brain to organize events in space.
Yeah.
And it has huge pro-survival characteristics to it, because if the brain tried to organize neuronal changes in its network along any of the other three axes, the world would look random. There would be no survival value to that, and the organism would be extinct before it could even get out of its egg. Yeah. So, in a way, we're creating an explanation for the world that is kind of a circular explanation, thanks to the way the brain likes to interpret information and changes in states. But as I showed you with the changes in the number of species going up the side of a mountain, there are other things that change in space that have nothing to do with time and are just as good as organizing nature as time is.
And we use them. Yeah.
And that's absolutely right.
One way of looking at the atomic the way atomic clocks work, the periodicity of the mechanisms that drive atomic clocks is that they are generating a predictable sequence of relics, essentially.
Yeah.
That we then use.
Yes.
Yeah.
And we use those oscillations as tags for other things in our world.
Yeah.
And because, and this is where it gets really interesting, because entropy is increasing in the universe, we can guarantee that the way that these states change is in the direction of more complexity, and that's a very favorable thing for living things. If there was less complexity going forward, we would eventually starve to death. There would be no...
The universe would die with a whimper, right?
There would be no net sources of negative entropy that we could tap onto as food. Yeah. Now, the interesting thing about this whole issue of entropy is that, the Big Bang, you would think the Big Bang was extremely hot, extremely random, and entropy should have been huge at the Big Bang. Absolutely huge. Now it's very cold. The universe is very cold. So the entropy of the universe should be very low right now because the universe is only 3 degrees above absolute zero. It turns out that there's a missing ingredient, and this is fascinating. It turns out that black holes carry information, and the areas of their event horizons are proportional to the entropy that they have. It turns out that there is more entropy in one supermassive black hole than the entropy of the original Big Bang. So the Big Bang was actually a very low entropy situation, even though it was hotter than hell, because of all these black holes that have now appeared in the scene, whose event horizons now basically code entropy information. The amount of entropy in a black hole is proportional to its area in Planck units. Okay, so it's huge. Absolutely huge. A single black hole can have more entropy than a good portion of the Big Bang. So the entropy of the universe when it was born was very, very, very low compared to what it is now, thanks to all of these black holes. So that resolves this whole conundrum of, well, why is entropy in the universe increasing? It's increasing because of the formation of all these dang black holes. And as a result, time is going in the direction of the formation of more of these event horizons. So that's why time is moving in the direction of increasing entropy as well. So that's the direction in which states are changing in the largest numbers, thanks to black holes. So it's all black holes all the way.
So we should look with gratitude towards the center of Sagittarius, right?
Yeah.
Well, I'm afraid your time's up, Sten.
Yeah, but it looks like it's like 8:20 now. Sorry about that, guys.
That was a joke, actually. But
I guess unintended. Yeah.
So I want to thank you, and I wish you well with your books, and your multiple interests going forward. And we had somebody here, Irene, she said, I have Ravelli's book on time, and now I will be ordering Sten's. Thanks for this fascinating presentation.
I have read so many of these books written by some of the most brilliant theorists of the time. And as an astrophysicist and astronomer, I find them so confusing. This is a confession.
Oh, good.
It's like I can hang on to their arguments up to a point, and then it seems like it gets lost in this weird semantics that I just simply can't penetrate. And it's not language. I mean, I understand the nouns and verbs that they're using, and in physics and quantum theory and stuff like that. But and that's why I wrote this book, because it's my way of trying to sort this out for myself. I even wrote an article for Astronomy Magazine a couple of years ago on the subject. And, I spent like 5 months, deep in the Vulcan Plak Tau of trying to sort out all of these different ideas. And, it was like, luckily I wasn't, sort of measuring my blood pressure at the same time.
Well, we were all benefiting from your translation, if you will.
And my chaos. Yeah. I think what I understand about it now is mostly correct and aligned with what the physicists are saying. But it still doesn't resolve the ultimate conundrum of, what the hell is this thing? And unfortunately, the only answer that I have is this damnable anthropocentric or anthropic principle that, the explanation for why time is so weird is because we're here. It's the ultimate refutation of scientific research, where the observer isn't supposed to be part of the experiment, to influence what's going on. But that happens in quantum mechanics all the time.
Sure.
We get entangled with all kinds of stuff when we make measurements, and we just hope that we can make, as little entanglement as possible so we can get at the true nature of things. But in relativity, you can never untangle yourself from anything in the world. That the observer is always a part of things. And in fact, the properties of electrons are not determined until the observer builds an instrument and makes a measurement. There is no fundamental reality in quantum mechanics. It's all dependent on what kind of a question you ask the system. And if you ask the system a question that's a particle-like question, you're going to get a particle-like answer. But if you ask it a wave-like question, you're going to get a wave-like answer. And the electron doesn't know which of these two you're going to ask it until after the observation. Before that observation, the electron has no properties at all. I mean, what do you make of that? To me, it's a freaking headache as an astrophysicist. I'm lucky that I don't deal with quantum mechanics because I just use it as a tool. Thank you very much. Anyway, I'm sorry. I'm just venting. I'm 72 years old, and I'm kind of crotchety about physics. And I thought we would be farther along with things than we are. And now we're just still muddling along like my freshman paper in astronomy class.
Well, I'm sorry we can't help you.
I was hoping for some insight from you guys. I guess this is the best we can do.
Forget about it.
We're all entangled.
Yeah.
Space is the final frontier.
All right.
Thank you so much for an enjoyable evening.
Thank you,
Have a
Sten.
great one.
Thank you.
Well.
It really was fascinating. Thank you so much.
Thank you.
Bye,
And as
Bill.
always, thank